TRL TRM calibration is a new feature on the PicoVNA 108. I'm going to assume that it's fairly new subject for you, the viewers, too. So I'm going to deal with TRL and TRM in two parts. Part 1 will address the act of calibrating the PicoVNA 108, and in the second half we'll take a close look at some measurements using that TRL TRM calibration. Focusing first on part 1, I'll introduce the calibration technique and a PCB that we've prepared for the demonstration. We're going to define and load a TRL TRM.kit file, and then we're going to perform the calibration. We'll also include a little discussion as to whether a TRL calibration is insertable or non-insertable. With that, let's move forward. Hello, in this video I want to take you through some of the TRL calibration facilities on the PicoVNA 108. To do that, I'm going to have to introduce you to this PCB because TRL calibration is a method by which primarily we're going to be able to calibrate for the measurement of devices that are mounted on a substrate. TRL is also used for very high precision calibrations, but that's not the story today. So let me introduce you to this PCB. On here I've got two devices that I wish to measure, both mounted on the substrate, and both are fed by identical feed lines on the two sides. Identical feed line, identical, identical, identical. So we have the same feed lines in each case. Now, to use TRL calibration on a substrate like this, what we want to do is we want to calibrate at reference planes right on the pads of the devices that we wish to measure. And to do that, we provide calibration standards on the same substrate and on the same feed lengths. Here's one of them. This is a Thru. It's a zero length Thru, right in the middle there, with identical feed lines on either side. Here are my two shorts in this case, could be opens, but here are my two shorts that I'm going to use today. And then there's a delay line here, which is basically made up of the same elements as a Thru, but with a little extra line length in the middle there. And in fact the length is about 10 millimeters. And it's those standards that support TRL, or through, reflect and line. Through, reflect and line calibration. That calibration is going to rely on the line length here to define a band of frequencies. We're not going to be able to calibrate at low frequencies using lines of these lengths, and at low frequencies lines tend to get very long indeed, so we do need an alternative method at low frequency, and for that we're going to use TRM, through, reflect and match. So we've already got our through and our reflects, but here we have two matches as well. So with those standards mounted on the same substrate, we're going to be able to first of all calibrate on substrate at reference planes right up against the midpoint of the through, the points of the short, the points of the load, and the points of the delay line that sits in the two feeders here. Now you could argue that in order to calibrate on this board to measure these two dots, I could have placed quite ordinary shorts, opens, load and through a salt calibration kit, and indeed I could. And indeed this is an example in which we do this. This is our network metrology training board, and on here I've got calibration loads and shorts and opens, and I've got up here a calibration through. So yes, indeed I could calibrate using these. The problem is that I do need to know the characteristics of these items, the load, the short, the open and the through. I need to know them quite well, all the way up to the frequencies of interest, which in this case with this VNA up to 8.5 gigahertz. And I need those devices to be reasonably good, all the way up to high frequency. And therein lies the problem. When we use a TRL calibration, we're going to rely instead on the qualities of the through and the delay at high frequency to achieve our calibration, and we're going to place less demand upon our knowledge of the shorts, less demand on our knowledge of the loads. They are going to be used primarily to do calibration at low frequency. At high frequencies, the shorts will need to be in the right place, but they don't need to be particularly good. They just need to provide a relatively high reflection. Likewise, if we used opens instead. So the advantages of TRL are that we don't need to know our components, our standards on this board anywhere near as well as we do if they were short open loads and short open load and through. Okay, so before we start talking too much about TRL calibration, I want first to find out a little bit about this board that we're going to use here. So in the first instance, I performed a perfectly ordinary cal at these PC 3.5 interfaces, such that I can measure the characteristics of all of these items from SMA through to SMA connector. And here is the display of both the line that I'm currently measuring, that's the blue trace, and earlier I measured the through and saved that, that's the yellow trace. And what I want to look at here, first of all, on the S11 plot to the top left, we can see that match. It's very good at low frequency, not bad at high frequency, and certainly by marker 1, which is a 1 gigahertz marker, at that point it's minus 45 odd dB there, so nearly 50 dB, so a very good match indeed. Looking at the S21 plot, top right, we can see that the through has less loss than the line. That's not surprising, the line is slightly longer. The two plots that are slightly of more interest to me are the ones at the bottom. First of all, on the lower left, I've got a time domain plot that gives me a readout on the right there of the impedance of the line. So markers 3 and 4 are both on the line, and what have I got there? I've got marker 3, it's sitting at 49.5 ohms. Marker 4 is sitting at 49.3. We will just have a look. If I just take marker 3 and I put that onto the memory trace, we can see marker 3 now is 48.9. So Here I can see that between two similar lines I do have a slightly different impedance of line on those two lines. It's really the impedance of the blue one that we're interested in. Oops. Back to data. 49.6 ohms there. We can of course see that our blue trace, the line is slightly longer than the yellow trace, the trace for the through. But we can measure this more accurately if we come across to this group delay plot on the right hand side here, and I'm particularly noticing here that group delay is reasonably flat across the whole length or across the whole spectrum that I've got of interest here. At 6 gigs I'm measuring, sorry, at marker 6, 4 gigahertz, I'm measuring a group delay of 272 picoseconds. And if we move that marker onto the memory trace, we can see that we have marker 6, 218 picoseconds there on the through. And what's of interest there is that difference between the two. Let's just have a quick look at the two loads. So looking at the match on the two loads, we just note here at 1 gigahertz we're less than 35, minus 35 dB, and likewise over here. So these two matches are fairly good at low frequency. You can see they decline somewhat at higher frequencies. Okay, so let's remind ourselves of what we've learned about this board. We have through, reflect and a single line standards. Our single line will define a single high frequency calibration band. And for a low frequency band we have resistive matches. We have all of those calibration standards on the same substrate and on the same feed lines as our DUT. The through transit time is 218 picoseconds, more or less constant with frequency. The matches are good, minus 35 dB out to 1.2 gigahertz, perhaps not so great at 2 gigahertz at minus 30 dB. The line is longer than the through by 54 picoseconds, which incidentally pans out to a propagation velocity of 62% C. It's about right for FR4. And the line impedance is just a little bit off ideal of 50 ohms. It reads 49.5. And we're going to need those numbers as we move forward. Okay, well, we now know enough to perform a TRL calibration. First thing we need to do is create a TRL kit for the standards that we have on our board. So let's do that. Tools, calibration kit, and then kit edit. Okay, well, for those of you that are familiar with this CalKit editor tool, you will see that we now have over on the right here a new section for information relating to the TRL standards. So we're about to create a TRL and TRM kit. In this case we are not going to be using load data, through data or short open data, so we'll untick those boxes and we'll leave them unticked. Over here we are going to use a single line length, and we know from our measurements earlier that the line length is 54 picoseconds. You can see that we have the option to use a second line here to define a second frequency band, but that we don't have two lines on our board, so we'll leave that unticked. And from this we can compute the frequency span that our calibration will be able to support based on that one line length. So computing from the delay, we see we have a band of 7.97 gigahertz down to 1.29 gigahertz. Those two numbers come about. We are looking to use our line to calibrate a frequency band, ensuring that we do not approach phase wrap points for the wave in the line. So this figure here tells us that 54 picoseconds of line will leave us with 150 degrees of phase shift at 7.97 gigahertz. This one is that 54 picoseconds of line will give us 30 degrees of phase shift at 1.29 gigahertz. So we're giving ourselves margins of 30 degrees of phase to stay away from the phase wrap points in that line length. Now, so these two figures are the maximum span that line can realistically support. If we were using two lines, we might want to overlap the two lines and keep those phase margins a little bit higher than 30 degrees. So we might choose to change these frequencies to values within that range, but with slightly higher margins. But I'm quite happy that we'll use this one out to nearly 8 gigahertz. I'm also very happy that we saw when we measured the match of our TRM loads on our board, we saw that we had about minus 35 dB of match at 1.2 gigahertz. So I'm fairly happy to continue with that lower value there. Down here, we have to select whether we are using shorts or opens as our reflection standard, and as you recall, we've got shorts on our board, so we'll leave that one selected there. And over here, given that it's a short, we can give some information about the inductance of that short. Now, in this case, it's a via at the end of a line through to a ground plane, and my estimate for inductance of that via is 100 picohenries. Now it might be that you have better values than that, say from the CAD computer-aided design files for the board. You may have a better understanding of inductance of vias, in which case you put in a better value there. Had we selected opens here, we would need to be telling the system something about the capacitance values for the opens, and likewise your CAD might give you a good estimate of fringing capacitance at the end of your open line. Okay, so we have completed the entry for this kit. We save it as TRL video will be the name of our kit, and we will save the kit. Save. We can close that. If we come back to the CalKit selection menu, we can see that currently we have eCal units selected to port 1 and 2. In order to perform a TRL calibration, we're going to now change that. We're going to load port 1 kit, and TRL video kit. There it is. Open. And I don't need to, but I will load it to port 2.2. And you can see that it's this page now reflects the values that we entered for our kit. Apply. Close that menu. So we've loaded our TRL calibration kit. We're now ready to perform a TRL calibration. So stop the sweep. And as we always do, first to check that the kit loaded to the ports is appropriate, TRL video kit. We are going to perform an insertable .TRL TRM calibration. So, question is this calibration an insertable calibration? Well, yes it is. If we remind ourselves by looking at the board, we are going to be calibrating at reference planes in the middle of this through. And so there we have a through connection of our two test ports right there in the middle. Then what we're going to do is we're going to split the two test ports apart and insert our dot. So yes, this is an insertable calibration, in that the two test ports, we can remove the dot and we could join them back together directly without any adapter in this through. So this is an insertable dot calibration, and indeed all TRL calibrations are insertable dot by their very nature. So yes, we've selected the right calibration here, and the astute might notice already that these buttons that we usually use to perform the calibration have changed. We now, instead of seeing short open loads and throughs on these buttons, we have got line, reflect, load and through. Okay, before we proceed with this calibration, you may recall that the line on my board will only support a span up to 7.97 gigahertz. At the moment, our span is exceeding that up to 8.5 gigahertz. So were I to try and start, I would be reminded that my cal kit does not support this frequency range. So we need to change things. So it's a TDR calibration that we're doing. I'm going to keep my 1024 points. I'm going to lower that to 7. Okay, so apply. We've applied our new span. We can now begin a calibration within the range of our cal kit. Connect line 1. Now, line 1 is our delay. Let's get that connected. Okay. Connect the high reflection standards. So those will be the shorts. Through. And the load. And there we are, that completes the calibration operation. So apply the calibration. So having completed the calibration, we are indeed ready to make some measurements, and that we'll do in part 2.